Okay, hello everybody. This is the second half of today's lecture in topological vector spaces. The lecture was interrupted for technical reasons, so we had to move to a different room, and there was no live stream from there. But I know that many of you prefer following my lectures online, and that's why I'm recording this the remaining part of the lecture again now. Just for your convenience. Okay, so the lecture was interrupted when we tried to prove the following technical lemma. Suppose that X and Y are locally convex spaces, and suppose that phi is a binuclear continuous linear map from X to Y. Let's recall that binuclear means that it can be factorized as the composition of two nuclear operators. The first operator acts from X to another space Z, and the second one acts from Z to Y. Also, suppose that Y1 is a closed vector subspace of Y, and assume that the range of phi is contained in Y1. Phi of X is contained in Y1. I claim that in this situation, phi will be a nuclear map from X to Y1. So to say this a little bit more formally, let's consider a map phi 0, which acts from X to Y1, and it acts exactly as phi 0. Exactly as phi. So phi 0 of X equals phi of X for every X. So basically, this is the same map of phi, but we consider phi as a map from X to Y1. So I claim that phi 0 is nuclear. Actually, this lemma is the main reason why we need binuclear operators. So let's recall that if we replace here binuclear, sorry, if we consider nuclear maps here instead of binuclear maps, then the result fails. And there is a respective exercise in our last exercise sheet. So if phi is nuclear from X to Y, and its range is contained in Y1, then it is not necessarily a nuclear map from X to Y1. But if phi is binuclear, then everything is okay. To prove the lemma, we use actually the same trick, which we have already used when we proved the stability of the class of nuclear spaces under standard operations. Namely, we factorize something nuclear through a Hilbert space. So more exactly, let's look at the following picture. So phi is phi can be written as a composition of phi 2 and phi 1, and they are nuclear. Phi 1, phi 2 are nuclear. And we look at the following picture. So this is X. This is phi 1. It acts from X to some space Z. Phi 1. And we factorize phi 2 through a Hilbert space. So we have a Hilbert space H here, and two maps, say alpha and beta, such that phi 2 is their composition. This is phi 2. We also have our closed subspace Y1 here, and we have the inclusion map, was denoted by I. And we do the following. We define a closed subspace H1 of H. H1 is just the preimage of Y1 under beta. It is contained, this is closed subspace of H. So we have the inclusion map here, was denoted by J. And let's denote by beta 1 the restriction of beta to H1. Okay, now since phi of x is contained in Y1, so we have this condition here. It follows that if we now look at the composition of alpha and phi 1, if we look at this map, its range is contained in H1, just by definition. So alpha phi 1 of x is contained in H1. So we this means that we can consider a map, was denoted by gamma from X to H1, such that the diagram commutes. There exists a map gamma such that J gamma equals alpha phi 1. And if we look at this diagram, we see that our map phi 0, which acts from X to Y1, is nothing but the composition of gamma and beta 1. Because if we compose it with the inclusion map, what we get is exactly phi. So phi 0 is just gamma composed with beta 1. Phi 0 is beta 1 gamma. And we want to show that phi 0 is nuclear. And to show that phi 0 is nuclear, we have it suffices to show that gamma is nuclear. And why is gamma nuclear? Well, gamma acts to H1, and H1 is a closed subspace of the Hilbert space H. And so we can consider the orthogonal projection here, P. Let P denote the orthogonal projection of H onto H1. Then gamma can be written as Pj gamma, simply because Pj is 1, is the identity map. But on the other hand, J gamma is J gamma is alpha phi 1. So this is P alpha phi 1. But phi 1 is nuclear. Phi 1 is nuclear, so this composition is also nuclear. So we conclude that gamma is nuclear, and because of this equality, we conclude that phi 0 is also nuclear. Phi 0 is nuclear. And this completes the proof of our lemma. Okay, now we can prove the following technical result, the following theorem, which will be one of the main steps in our approach to the Cartan-Serre finiteness theorem. And actually, this result is useful in other situations as well. Suppose we have two co-chain complexes, C and D, two co-chain complexes of Fréchet spaces. And suppose that phi is a binuclear quasi-isomorphism between C and D, from C to D, a binuclear quasi-isomorphism. I claim that in this case, the cohomology of C, or equivalently cohomology of D, they are isomorphic, are finite dimensional. Hn of C, or equivalently Hn of D, is finite dimensional. The proof will be based on the previous lemma and on our baby version of the Schwarz theorem on nuclear perturbations. So I'd like to recall once again that the original version of Schwarz theorem was about compact perturbations. But for our purposes, it suffices to consider a simplified version of the Schwarz theorem, which is about nuclear perturbations. And the proof of this result was essentially easier than the proof of the original version of the Schwarz theorem. Okay, so let's look on the following picture. So this is Cn minus 1. The differential of the complex C takes Cn minus 1 to the subspace of n cocycles, which will be denoted by Zn of C. It is contained in Cn. And let's denote this map by d n minus 1, or better, d bar as n minus 1. So this is actually the differential of C, but we consider this differential as a map from Cn as n minus 1 to the space of n-dimensional cocycles of C. And we have a similar picture for the complex D, dn minus 1, Zn of D, which is contained in Dn. And here we have d bar n minus 1. Okay, now here we have the map phi n minus 1. And here we have phi n. Let's denote by phi n bar the restriction of phi n to the to Zn of C, to the space of n cocycles. By assumption, phi n is binuclear. Phi n is binuclear. And when we compose phi n with this inclusion of Zn of C into Cn, this map is also binuclear. And so we are in the situation of our previous lemma, which implies that phi n bar is nuclear. So the previous lemma implies that phi n bar is nuclear. Okay, and let's now use the assumption that phi is a quasi-isomorphism. So it induces an isomorphism in cohomology, and in particular, it is surjective in cohomology. What does that mean? This means that every n cocycle here in Zn of D comes from an n cocycle here, modulo a co-boundary. This can be stated explicitly as follows. Let's consider the following map phi, F, which acts from the direct sum of dn minus 1 plus Zn of C to Zn of D. And this is this map can be written as the direct sum of d bar n minus 1 plus phi n bar. So more exactly, this means that this map F takes each pair x and y to the sum of the elements d bar n minus 1 of x plus phi n bar of y. This is our map. And since phi is a quasi-isomorphism, it follows that phi is surjective. Phi is, F is surjective. That is, once again, every n cocycle here comes from an n cocycle here, modulo a co-boundary which comes from here. So this means exactly that F is surjective. Okay, so we are almost in the setting of our version of the Schwarz theorem. So F is a surjective map between Frouchet spaces. This is a Frouchet space. This is also a Frouchet space, and F is a surjective map. And now we consider a nuclear perturbation of F. And where is the nuclear perturbation? Here it is, phi m bar, or more precisely, 0 plus phi m bar acts between the same spaces. And it is obviously nuclear, because phi n bar is nuclear. So this implies, if we now apply the Schwarz perturbation theorem, that the co-kernel of F minus 0 plus phi n bar is finite dimensional. It's finite dimensional. But what is this map? F minus 0 plus phi n bar. So we'll look once again at F. This is F. So basically, this map acts by 0 on the second summand, and it acts as dn minus 1 on the first summand. So the co-kernel of this map is isomorphic to the co-kernel of dn bar. Sorry, dn minus 1 bar. So the images, the ranges of these two maps are the same, and so their co-kernels are isomorphic. But what is the co-kernel of dn minus 1? So this is dn minus 1. Clearly, the co-kernel of this map is nothing but the nth cohomology of the complex D. So this is Hn of D. And that's it. So we see that cohomology of the complex D is finite dimensional. This completes the proof. Okay, so now we are almost ready to prove the Cartan-Serre finiteness theorem. The only little thing to before the proof is a simple exercise for you, a simple exercise in complex analysis. If X is a complex manifold, and if U and V are two Stein open sets in X, Stein open sets, then their intersection is also Stein. Okay, so now we are ready to prove the Cartan-Serre finiteness theorem. And actually the proof will be very short, modulo what we already know. So what we want to do is to show that if X is a compact complex manifold, then the cohomology spaces of any coherent analytic sheaf on this manifold, the cohomology is finite dimensional. Okay, so let's choose two open covers. Let U and V be finite open covers. Finite open covers of X, such that V is a refinement of U in the following strong sense, such that for every set V in V, there is a set U in the first cover, script U, such that the closure of V is contained in U. So in particular, V is a refinement of U, but the point is that we put the closure here. So we can consider now the refinement map, which acts from the Czech complex corresponding to U to the Czech complex corresponding to V. So this map was denoted by phi star. Phi star, this is the refinement morphism. So we'll consider its nth component. And let's observe that this map is binuclear. So why is it so? If we compose it with one of the projections, so Cn is a finite product of finite many section spaces. Oh, sorry, I forgot to explain maybe this. I should explain this in more detail. Why such open covers exist, and they do exist for the following reason. First, we take an open cover, an arbitrary open cover U, and choose another open cover satisfying V, satisfying this condition. This is just a topological argument. And finally, we observe that since X is compact, we can choose finite subcovers, and this is exactly what we want here. So such covers U and V always exist. Good. So now we come back to this map. I want to show that it is binuclear. We compose it with the projections onto the direct factors. So this is F, section space of F over the open set corresponding to finite linear indices J0 to Jn, say. And by the definition of this refining morphism, this map is factorized through the section space of F over U corresponding to I0 to In, where each index ik is just phi of jk, and phi is the refinement map, which takes Vj to takes j to phi of j, such that Vj is contained, the closure of Vj is contained in U phi of j. This is just the construction of our phi. Okay, so and here we have the restriction map. Well, but we already observed, this was a little exercise for you, that this restriction map is binuclear. And this easily implies, this is again a little exercise, that this implies that phi star n is also binuclear. Well, basically this follows from the fact that these restriction maps are binuclear, and from the fact that Cn is a finite product of these section spaces. So phi star is binuclear, but on the other hand, we have the second Leray theorem, Leray 2, which implies that phi star is a quasi-isomorphism. Well, why is it quasi-isomorphism? Let's recall that the Leray theorem states that if U and V are cyclic for F, then it's a quasi-isomorphism. But they are indeed cyclic because they consist of Stein open sets. And by our previous exercise, all finite intersections which appear in this diagram are also F is also acyclic on each of these finite intersections by theorem B, by Cartan's theorem B. So it's a quasi-isomorphism because U and V are acyclic covers for F by Cartan's theorem B. And by the exercise. that is, finite intersections are also Stein sets. Okay, so here are cyclic covers. So phi star is quasi-isomorphism, and then we apply our previous theorem and conclude that the cohomology of our Čech complexes is finite dimensional. It's finite dimensional. But we also have the first other theorem, which states that since the open cover U is a cyclic for F, it follows that the cohomology of the Čech complex is isomorphic to the cohomology of the sheaf F. And we see that, as a result, we see that the cohomology of F is finite dimensional. And this completes the proof of the Gartancer finiteness theorem. And this is the end of our course. So thank you. In conclusion, I must only say that, of course, our course is not complete, because any good course in topological vector spaces definitely must include an introduction to the duality theory for locally convex spaces. This is a very useful part of the whole theory, which involves many interesting results and constructions, McKee topology, bipolar theorem, and many other interesting results. So unfortunately, we had no time to discuss this subject, the duality theory for locally convex spaces. But on the other hand, this subject is fairly standard, and you can find it in almost all standard textbooks in topological vector spaces, like, for example, Scheffer's textbook, or a textbook by Robertson and Robertson, and many other good texts are also available. Okay, thank you once again, and this is the end of our course.